Hi, folks. Do we have a? Can you all hear me? Fine.
Yes.
Yeah. Okay. Okay. So this is a new package I've been working on. This is an introduction to Valkey-Swift. So this is Valkey-Swift is a client, a Swift client for Valkey, surprisingly. Well, first, what is Valkey? Valkey is Tim, my notes aren't appearing. Sorry. Valkey is an in-memory data store anyway. It provides, it provides microsecond access. Oh, there you go. Yeah. Yeah.
We'll cut that. It's fine.
Yeah, provides microsecond latency on rich data structures. It's primarily used as a key value data store. It can be used as a caching layer for databases, for temporary storage, and is also used for message queues. If this all sounds quite familiar, that's because Valkey, whoops, back. Oh, sorry. Valkey is a fork of Redis. Redis 7.2.4 precisely, which was released in 2024. So why did I decide I was going to develop this? We already have a Redis client, don't we? Well, during the process for upgrading the Hummingbird project towards Swift concurrency, we struggled to resolve issues with two of our packages which use Redis. Redis Stack is not a very friendly package when it comes to Swift concurrency. We struggled to integrate it. We had made nasty workarounds. We used pre-concurrency. And at the time, I was like, well, I'll just have to survive with that, and we'll wait, and it'll get resolved. 12 months later, nothing had changed. So I decided I would have to do something about it. And this is where Valkey-Swift comes in. Second question, I suppose, is why Valkey? Redis has considerably more installs, but Valkey has the momentum. The major cloud providers are promoting Valkey over Redis, and Valkey-Swift was for looking towards the future. So what were my initial goals when starting out the package? Full integration with Swift concurrency. What does this mean, though? Obviously, it means using async functions, no more event loop futures. Types should be sendable where applicable. I don't want Swift 6 telling me I can't send my client between tasks. It also should be a good citizen in the world of task cancellation. If my task is cancelled and I'm in the middle of processing a Valkey command, I should jump out immediately. And then finally, it should use structured concurrency to help manage the lifetimes of resources. Second goal was to support all the Valkey commands. I don't want the client to hold back people from usage of Valkey. So what did we build? Well, we covered everything in the previous slide, and we built quite a bit more. For the following slides, I hope to cover some of what we did. So we have a client library. We need a client type, and we named it Valkey Client, of course. This is us creating a client. You create a logger. You provide it to the client along with a network address and some configuration. And then all the Valkey commands are available directly from that client. Here we are setting the value associated with a key and then getting it back. Probably the two most popular commands. But what happens when you call a command? Well, the Valkey client is backed by a persistent connection manager. This manages a pool of connections. It's each call will release a connection from the connection pool, and once it's finished, it will release that connection back to the connection pool. This means we don't need to establish a new connection for each command, and it minimizes time and resources to run commands. The Valkey client connection manager does require a background process, though, to run. There's two possible methods for running this. Would be, well, one, using a task group. Here we create a task group, add a task which runs the background process, and then we run our application. This is probably, if you were using a Vapor application, this is probably the easiest way to do it. And as an alternative, you can use a Swift service lifecycle. Here we are running a service group which includes Valkey client and an HTTP server. So far, we've covered calling commands directly from the client, but each call releases a connection, and you can't be guaranteed that from one call to the next that you're using the same connection. If you're in a situation where you need to ensure commands run on the same connection, we supply a method to lease connections called with connection. Here you can see us calling with connection. You provide it with a closure which gets given the connection, and then you run your commands. Again, all the commands are available on the connection as well. And as soon as you exit the closure, the connection is returned back to the connection pool. This is an example of using structured concurrency to manage life cycles of resources. So I said we were going to support all the Valkey commands, and yes, we do. We support all the data types: strings, numbers, bit sets, lists, sets, sorted sets, hash tables, streams, and everything else. We support other functionality like scripts, functions, transactions, and pub/sub. And then we support all the system commands for setup of clients and servers, and then authentication and supporting the high availability modes of Cluster and Sentinel. That's over 400 commands. So did I write wrapper functions for all 400 of those commands? No, I'm too lazy. So what I did was I wrote a code generator. Anyone who's experienced has used my Soto package will know I have experience in this. Luckily, Valkey provide JSON files that describe every command. We collate all of these files into one big file and then feed it into a code generator that we built. And then out of that, we get two different sections of code. First, we'll show you. This is the HTML. This is the JSON that you might get for a simple command. This is string len. You get some metadata. You get like a description of the return value and description of the arguments. And then this will generate first a Valkey command type, which includes pretty much all the same information, and then an encode function at the bottom. And then the function that you would call. And you can see there it just calls execute on the command type. Because we use code generation, we are also in a position where we're quick to respond to changes in Valkey. The version 9 release candidate was just released a couple of weeks back. I added all the new command changes in about a minute by just running the code generator again. Okay, now we're on to parts of the project which were not in our initial goals. Pipelining. What is pipelining? Pipelining is sending multiple commands to the server at the same time without waiting for the response to each individual command. It's a technique for improving performance for both client and server. It removes the round trip for the cost of individual requests, and it also reduces the number of reads and writes that the server has to make. I drew you a little graph to explain the advantages. If you imagine time going from the top to the bottom of this graph, you can see on the non-pipelined example that are sending a request from the client to Valkey, and it responding with a response. We wait for the response, send the next request. Valkey responds with a new response, and so on and so on. With pipelining, you can send all the requests at the same time and get all the responses back at the same time, thus improving performance considerably. So this is a code example where we're pipelining. You can see in the middle, you can see the two Valkey commands that we use there. That's the types. We use the types in this situation. So there's a set where we set a key, and then there's an incre, which is basically increments that value. Then these are passed to an execute command. I'm going to show you the signature of the execute command because it'd be easier to explain while the signature is up. Basically, execute takes a parameter pack of Valkey commands and then returns the result, a parameter pack of results containing the responses for those Valkey commands. So you can see in this example here we have we're checking the increment response from the return by the execute, and that is already that's already an integer. It's not a generic value. And we add a little Swift testing bit in there just to verify. Pipelining also comes into play with Swift concurrency. The Valkey connection is sendable, so that means you can share it across multiple tasks, which means you can send commands from multiple tasks at different times and not worry about what the state is of the commands on other tasks. As you can see in the graph, there's multiple requests being sent off, and then the responses coming back as and when they're ready. The only warning I would say with using this method is the order that you send requests out is the order that the responses will come back in. So if you send a blocking command out, every response after that will wait until that blocking command releases. So here's a quick code example of us using async let to create 4 tasks, all setting different keys. Obviously, you can use the task groups, which this is a shortcut for anyway. This can give you considerable performance improvements. As an extreme example, when benchmarking the library on my laptop here, with one connection and 1,000 concurrent child tasks, it's possible to send and receive the responses for over 120,000 commands a second. I'm just going to get a glass of water. PubSub. Valkey-Swift provides support for the Valkey publish-subscribe messaging model. It's fairly simple. You can subscribe to a channel and then receive all the messages that are published to that channel. You can subscribe to a pattern and receive all the messages to channels whose name match that pattern. Publishing publishing is a fairly simple operation. It's just a simple command. Here we have a channel, ServerSide.swift, events, and a message, which is Valkey-Swift talk starts. Subscribe is a bit more complex. You supply a list of channels you're interested in and a closure that will receive an async sequence of subscribe events or publish events. This again is another, and then you can iterate over those events. Here we just print them to the log. This is another example of using structured concurrency to manage resources. Before we enter the subscribe closure, a subscribe command is sent to the connection, and when we exit, an unsubscribe command is sent. There's no way you can leave that code and still have your connection subscribed to the channels that you were listed. Another thing to note in this code example as well is also subscribe's available both off a connection and off the client. If you call it from the client, it will use a shared connection which all calls the Valkey client.subscribe will use, thus limiting the number of connections needed for subscribing to many channels. And similarly, you can subscribe to a pattern. This is pretty much the same code as before, except it's called psubscribe, and our pattern is anything prefixed with ServerSide.swift/. Valkey cluster. Cluster is a deployment for scaling horizontally. It splits the key space across multiple nodes, and each node is responsible for a subsection of that key space. If we look at some graphs, you can see here this is pretty standard. We send a command through the client to a single standalone Valkey server and get a response. But in cluster, we have multiple nodes. As I said, the key space is split across the nodes. The keys are, to split them, the way it's done is the keys are hashed into a value between 0 and 16,383. And then each of these values is called a hash slot. And then these hash slots are shared across the nodes. So in this case, you can see the first one is responsible from 0 to 5,460 and so on. Then the client receives the command, looks at the keys used by the command, works out the hash slot for the keys. In this case, the hash slot for foo is 12,182, so it selects the right node based off that, and then sends the command. Cluster also provides a level of high availability. Each primary server node has a number of replicas. As keys are updated on the primary, any changes made to the database are passed down to the replicas. Each node in the cluster is talking to each other, so if a replica finds its primary node has stopped communicating and it's considered in a fail state, then the replica can initiate a vote for it to be promoted to be the primary node for that shard. Remaining primary nodes will then vote on who should be the new primary node, and then the cluster can continue to serve the full key space. So how does Valkey-Swift deal with all this? Well, we have a special client first. It's a fairly similar setup, except that the network address is replaced by something called node discovery. And node discovery is basically returns a series of nodes. Here the library supplies a static node discovery type where you can just type in the IP addresses and ports. But you can also write your own node discovery type. So you could, in theory, write one that looks for all the Valkey nodes in your AWS account. So at startup, you start your client up. It goes out to discover the state of the cluster. It asks all the nodes it found in node discovery, can you tell me what the cluster looks like? And then using a voting mechanism decides on all the nodes that are considered existing by at least half of the nodes from the node discovery will be considered valid. Then the client will then maintain connection pools for all of these nodes and do regular background checks to make sure that its view of the cluster is the same as what is in reality. It then routes commands, as we saw earlier. And if the cluster client's view of the cluster topology is out of date, commands will return errors, and the client will respond to those errors and redirect requests to the correct node. As with the standard client, all the commands are available again. So this is where I do a demo. So I wanted to do a demo which involved more than just to show you that Valkey or Redis can be used as more than just a key value store. Because a demo showing a key value store would be a bit dull. So I'm going to create a chat server using 4 commands. Oh, and a Hummingbird server as well. I need my glasses on for this, though. OK. So I'll very quickly go over the structure for anyone who's not familiar with Hummingbird. In Hummingbird, we don't have a command line parser, so we use the standard Swift argument parser. And with that, we have a run command. You can see my cursor. In the run command, we build an application. And then from that application, we call run service. The helper text is quite useful here. Run service basically creates a Swift service lifecycle service group, which includes the application and then any child services attached to it. So if we go into look at the build application function, we create a logger, we create our client. The client's connecting to localhost. I should hopefully have a Docker. Yes, I do. I'm using Docker to run Valkey locally. We build a router for HTTP requests, and we build a router for WebSocket requests. And then we build our application using these 3. You can see here that we're adding the Valkey client as a service. The HTTP router is fairly basic. It's just loading in logging requests and then serving files. This is to serve the web pages for the chat server. The WebSocket router is where the good stuff happens. And so basically we have this chat controller, which is where we add the routes, or we get the route. We have one WebSocket route. WebSockets are split into 2 closures. You have a closure which is called during the upgrade process, where you can tell it to not upgrade, and then a closure which will handle the WebSocket once the upgrade has happened. Here, in our first closure, we're just checking to see if there's some query parameters available. So in the actual upgrade handler, though, it's called with an inbound stream of WebSocket frames, an outbound writer to write WebSocket frames to, and a context which we can get the request from. So we extract username and channel name from the request. And at this point, we create 2 tasks. At this point, I was going to say this version is only using 2 commands. It's using the publish pub/sub commands. So we basically read in WebSocket messages, and then we publish them to our channel for that. And then in the second task, we subscribe to that channel, and any events in that subscription, we will then write back out to the web client. So if I do a quick demo of it here, I'll make sure it's running actually, that would help. Yep, we're running. So we've got 2 clients here. If you look at the top, basically you're using query parameters to define. So we've basically got a username, Adam, that's me. And our channel is ServerSide.swift, so I connect. I'm logged in as Adam. Oh, Tim's joining us. So now if I type in here, hello, Tim, you'll see that it goes, he receives the message, and similarly in the other direction. One problem with this though, pub/sub has no persistent storage. You only receive messages if you're actually subscribed. So if I restart Tim's chat and he connects, he doesn't see any of the history. So we need some persistent storage. So what we're going to do is add some persistent storage. I'll put these down just now. First thing, we're going to use a Valkey stream. Valkey stream is a stream of events where each event has an ID and then a hash table. So we're going to replace this publish command with, if this better work. There you go. This is basically now using 2 pipeline commands. We still have the publish command here, but we've also added this xadd command, which adds an event to our stream. If you call ID selector auto ID, what it does is it sets the ID to be the number of milliseconds since 1970. And then we fill out our hash table with some useful information, i.e. username and message. So now when someone joins the chat server, they need to see the history. So we need to read what's in this stream. So first, we'll work out an ID, the ID to read from. We're going to use basically 10 minutes before now. So that's basically the number of milliseconds since 1970 until 10 minutes before now. And we call a function called xrange, which you give it the start ID for that time, and the plus will just basically go until the end of the list. We need to do something with these messages though. So let's write them to the WebSocket. So this is basically going through the list of messages, making sure they have the right fields, and then writing them out to the WebSocket. So if we rebuild, well, let's rebuild, have a drink. Yep. Let's connect again. This time round, I'll just anyone there. Now when Tim connects, you can see he receives the history. And so on. I did have a whole shtick with like I'd type a whole bunch of things where Tim would say great things about me, but I don't want to type in that. Now we go back. Can we back to? Actually, I don't think I really need the notes for the last bit. It's only one. I think this is one of the more important slides. Obviously, as I said earlier, Valkey is a fork of Redis. That means Valkey-Swift is fully compatible with Redis up until 7.2.4. And while Redis supports backward compatibility, which I don't see why they would not, it will support any 7.2.4 features in any Redis installation. This means you may have a Redis database set up already and you don't want to move, but that doesn't mean you can't give Valkey-Swift a try. And I thoroughly encourage you to do so. Thank you.